the properties of vector operations. Let's say you have three different vectors, u, v, and w, be vectors in a plane, so they have the same sign. They are two-dimensional vectors. And I have two scalars, r and s. Right? It doesn't matter the value of r and s, it's just the arbitrary scalars. Right? The first property is the commutative property. That is, if you do u plus v, you're going to get the same result as doing v plus u. For the associated property, if you do u plus v plus w, so it say that if you group these two vectors and perform vector addition first, and then add it with vector u, it's going to be equivalent to grouping u and v and perform that calculation first, and use the resulting vector added with w. So the both sides are going to be the same. Additive identity property, that is u plus the zero vectors going to give u as well. So it's nothing going to change when you add a vector with the zero vector. Additive inverse property, if you do u plus negative u, so if you do the vector additions on the opposite of the original vector itself, then you obtain the zero vector. Now, number 5, the associativity of scalar multiplications. So if you have two scalar r and s, you multiply them together, you have a new scalar, and apply that scalar on vector u. It's going to be the same if you scale the vector u first. Whatever new vector you have, you scale it again with the scalar r to get the same result. Or if you scale the vector u with the factor or with the scalar r, and then the resulting vector gets scaled again using s, you're gonna get the same answer. Now for distributive property, if you have r times u plus v, then is going to be equal to r times u plus r times v. So it say that if you perform the vector addition first and then scale the resulting vector, then it's going to be equivalent to scaling each vector first and then adding the results together. Now if you have two scalar add together and then multiply that or do scalar multiplication on vector u, so it say that let's add these two scalars together, you have a new scalar, and apply that scale on the vector u. It's going to be equivalent to scaling vector u with the r factor first, and then add with the scale vector of u with s, then it's going to be the same results. Now number 7, identity and zero properties. So if you have the vector u and you just do 1 times regular multiplications of the vector u, then you have the vector u itself. Okay, if you use 0, this is a scalar 0, not a zero vector. You multiply do regular multiplication on vector u, then you're going to have the zero vector at the end. So these are the properties of the vector operations, again including commutative property, associative property, distributive property, and some of the other properties that you're going to experience throughout this course. Alright, so I'm going to want to quickly perform a proof on commutative properties. Should be a very quick proof to do. Consider that u and v are just two-dimensional vectors. Now, consider vector u equal to u1, u2, and the vector v is equal to v1, v2. Then you do u plus v which is equal to u1, u2 plus v1, v2. So for vector addition, we see the definitions earlier. To get the first entry, you just add the u1 and v1 together, and for the second entry, you add u2 and v2 together. So u1 plus v1 comma u2 plus v2. And because in the regular additions, u1 plus v1 is going to be equal to v1 plus u1. So I'm going to rewrite that as v1 plus u1, and u2 plus v2 is equivalent to v2 plus u2. And now you can separate the resulting vector out into v1, v2 plus u1, u2. And by doing this, you show that the first vector is vector v, and the second vector is vector u. So therefore, we just basically show that the vector addition is commutative. Now, I want to show another proof here again. For the distributive property, it shouldn't be too difficult. So let's consider the two vectors u and v, but in this case, I want to include a scalar r as well. So consider u equal to u1, u2, and v is equal to v1, v2. And a scalar r. Then you have r times u plus r times v, given that u is equal to u1, u2, and v is equal to v1, v2. So r times u is the scalar multiplications, and r times v is also a scalar multiplications, and they are written in the component form. So you see the example earlier that to apply or to perform the scalar multiplications, you just basically multiply r, or the scalar or the factor, with each component of the vector. So for r times u, you have ru1 comma ru2. For r times v, you have rv1 comma rv2. And now this is the vector additions in the component form. So you get the result by adding the first components together and second components together. So ru1 plus rv1 comma ru2 plus rv2. For each component, as you can see, r is a common factor. So you take r as the common factor, and you get r times u1 plus v1, comma r times u2 plus v2, and therefore you can pull out the value r in front like this, and you have u1 plus v1, comma u2 plus v2. So these two results are equivalent to one another, because when you distribute r back, or you multiply or perform a scalar multiplication for this vector, you will go back to this result. Okay, and here this one is going to be u plus v, as you show in the last proof. So this one's going to be r times u plus v. So therefore, we just prove one of the distributive property. So those are the properties of vector operations. Now let's move on to some example here. So I would like to consider a vector with the initial point 2, 5 and the terminal point 8, 13, and also a vector w equal to -2, 4. So I would like to express v in the component form and find the magnitude of the vector v. So in this case, I use the notations of absolute value of the vector v. So in this case, this is the magnitude of the vector v. So here, or another notation here I mentioned earlier is the is to show the magnitude of vector v. So v in the component form, you get the x value of the terminal point, subtract the x value of the initial point, the y value of the terminal point, subtract the y value of the initial point, and you get 6, 8. And the magnitude of v is going to be equal to the square root of 6 squared plus a squared, or it's going to be 36 plus 64, but this is the square root of 100, or equal to 10, right? So it should be a positive number because we're talking about the magnitude. Now in part B, you want to perform the vector additions of the two vectors v and w. So v plus w equal to 6, 8 plus negative 2, 4. To get the result, you combine the two values of the first component together, so you get 6 plus negative 2, or 6 minus 2. And for the second entry, you combine the two values of 8 and 4 together, and the resulting value is 4, 12. So this is the value of the vector additions. In part C, you have both scalar multiplication and vector subtractions. So for 3v minus 2w, this is equal to 3 times 6, 8 minus 2 times w, which is negative 2, 4. First, you perform a scalar multiplications. So 3 times 6 and then 3 times a. So 3 times 6, you get that to be 18. 3 times a is 24. Plus, now you do scalar multiplications on vector w, and the scalar multiplication is negative 2. So negative 2 times negative 2 is positive 4. And negative 2 times positive 4 is negative 8. And instead of vector subtraction, now you have a vector additions. And you just perform the vector addition component-wise. So 18 plus 4 is 22, and 24 minus 8 is going to be 16. Now, there's a very special type of vector. It's called the unit vectors, and it's calculated as follows. For any non-zero vector v, the unit vector u of v is given as, so u in this case is the unit vector of the vector v, is equal to 1 over the magnitude of v multiplied with the vector v itself, or sometimes it is written as this in this form. Because u is the unit vector, the length of the unit vector is always equal to 1. So the unit vector, when you take the magnitude of that, is always equal to 1. And because u depends on the vector v, therefore the unit vector u has the same directions as v. And this equation I call equation star. So equation star is called a normalizations. So now let's move on to example 4. In this example, you have a vector of the form 1, 2, and you want to calculate the unit vector that have the same direction as v. Again, the unit vector always have the same direction as the original vector v. Alright, so the unit vector u is calculated as v divided by the magnitude of v. For the magnitude of v is calculated as, this is equal to square root of 1 square plus 2 square, or this is square root of 1 plus 4, or square root of 5. So the unit vector becomes 1, 2 divided by square root of 5. you can leave it like this is going to be the result, but most of the time the result is written in this form: 1 over square root of 5 times the vector 1 comma 2, and you can distribute 1 comma 2, or you can perform the scalar multiplications on the vector, and the resultant vector should be 1 over root 5 comma 2 over root 5. Now in part B, they ask you to find a vector W. So this is a brand new vector, and this brand new vector has the same directions as V, and the magnitude of the vector W has to be equal to 7. Okay, so you do here, since U, the magnitude of U is equal to 1 again, because U is a unit vector, then the magnitude of W equal to 7 can be written as 7 times 1, or 7 times the magnitude of U. And because of that, you can conclude that W is equal to 7 times U, which indicate that W has the same directions as V. Again, Y as V when W is equal to 7 times U, because U is the unit vector of V, and therefore U has the same direction as V. And W is equal to 7 times U, therefore it has to have the same direction as V. And the component form of W is 7 times 1 over root 5 comma 2 over root 5. Therefore the resultant vector is 7 over root 5 comma 14 over root 5. So let's move on to the next definition. It's called the standard unit vectors. So the standard unit vectors are the vectors for the axis, and so the standard unit vectors are the vectors of the form. So in this case, the standard unit vector, I'm going to use the notations of I hat. This is the vector of the form 1 comma 0. This is the unit. So this is the unit vector in the x directions, right, or on the x-axis right here. And another standard unit vector is j hat, is of the form 0 comma 1. This is the standard unit vector for the y-axis. Now this is quite important to know the standard unit vectors, because sometimes it's convenient for us to rewrite a vector, just any random vector, in terms of the standard unit vector instead of the component forms vector. Okay, so a vector V equal to x comma y can be expressed in terms of the standard unit vector form, or in the standard unit vector as, so we have V equal to x comma y, or if you separate this component form into x comma 0 plus 0 comma y, so basically if you add these two vectors together, you will get back to x comma y. And now for the first vector x comma 0, so x, let's say, is the scalar of the vector. When you pull the x out, you get x times 1 comma 0, right? And again, if you do perform the scalar multiplication on this vector, you will get back x comma 0. And for the second vector, y is the scalar of the vector 0 comma 1, or y times 0 comma 1. Okay, when you write it this way, V is equivalent to x times I hat plus y times j hat. So not only that you can write a vector in the component form x comma y, you can also express v, a vector v, or any vector for that matter, in terms of the standard unit vector. So in the next example, you have a vector u, which is the unit vector that forms an angle 60 degree with the positive x-axis. And then we want to actually calculate this vector u. Again, vector u in this case is considered to be a unit vector, and therefore the length of the vector u is equal to 1. And after calculating the component forms of u, you want to express this vector in terms of the standard unit vectors form. Alright, so here's the pictures that we want to consider. So this is the y-axis, this is the x-axis, and here is the origin. The vector u form an angle of 60 degree with the positive x-axis. So this is the positive x-axis, and this is the vector u form. So vector u form an angle of 60 degree. Okay, and again the unit vector, u is the unit vector, so therefore the magnitude of u is equal to 1, or the length of this vector is equal to 1. If you notice, from the head of the vector, you can project this onto the x-axis, and you can calculate the value of x and the value of y, or the component of u, using sine and cosine values. Alright, so this is the x value, or the first component of u. This is y, which is the second component of u. So for x is equal to, which is the adjacent side of the angle 60 degree, so cosine of 60 degree is equal to the adjacent x over the hypotenuse, and that is equal to 1. So therefore x is equal to cosine of 60 degree, and that is equal to 1/2. Now for y value, or the second component of the vector u, you do sine of 60 degree is equal to y divided by 1, right, or the opposite length divided by the hypotenuse, and therefore y is equal to sine of 60 degree, and that is equal to √3/2. So the vector u can be written in the component form as 1/2 comma √3/2, or it can be written in the standard unit vector form as 1/2 I hat plus √3/2 j hat. So that's it for me. So this is the lecture related to the vectors in the plan. So that is just two-dimensional vector. You can apply different vector operations on a two-dimensional vector, including scalar multiplications, vector addition, vector subtractions. We also talk about how to calculate a vector using the initial point and terminal point. We talk about how to calculate the magnitude of a vector. We have different properties of vectors operations. We also perform calculations on scalar multiplication and vector additions in the component form, and we calculate the unit vectors of a given vector. We talk about the standard unit vector. So in this case, the notations I had is for the unit vector, or the standard unit vector of the x-axis, and j hat is the standard unit vector of the y-axis. Not only that you can write a vector in the component form, but you can also express the vector in terms of standard unit vector forms. So that's it for me. Please let me know if you have any questions. Thank you.